Alrighty, ladies and gents, welcome to your lecture number 11 in the embedded system course. And we're still tackling the real-time operating system section of the RTES course. Alright, so up until now, we had a couple of hypotheses about the scheduling of the different tasks. We suppose that they are periodic, and by now everyone should be able to know how to create a periodic task, whatever the real-time operating system that you're using. And we said that the overhead of switching between the different tasks is 0, so there's no overhead by the kernel, and those two are still true. And the third one, we said that they're completely independent. All right, so now we're gonna check what happens when tasks are not independent, and a non-independent set of tasks means that they'll be sharing global resources. All right, so imagine that you see a schematic like that in somewhere, maybe in an exam, maybe in your job somewhere, right? So you need to start drawing conclusions that that you will get from the different information that you're having here. So for instance, we can we can say that here we have two different tasks. Apparently they're attempting to spit out a message on a display, and we can notice that those two tasks, because they share a display, these are dependent tasks, so they share a global resource, which is the LCD or the display of whatever that device here is. So this is the first conclusion: two tasks in the system, right? And the functionality of each of the tasks is to spit a different message. The first one is attempting to spit out bonjour, and the second one is trying to print out bonsoir. All right. The second thing that we can draw here is the execution scheme of the different tasks. So this has round robin written all over it, right? So it feels like there's a time slice dedicated for the first one, second one, third one, etc. And by now, using your experience in RTES and RTOS in particular, and FreeRTOS, you can assume that T1 and T2 share the same priority. Fair enough. And last thing that we can think of is, instead of spitting out a whole sentence or a whole word, apparently each task, each time it enters the CPU, it will print out only one character. Even though this doesn't really happen in real life, doesn't make any sense, but it's a good illustrative example to check. All right. So yeah, so if we're sharing without any kind of protection, what would happen? Well, as you can see it here, yeah, we'll be able to read gibberish, complete gibberish on the LCD or on the display, because there are no protection mechanism implemented in order to make sure that both messages do not overlap. And this is the point of today's recording. Alright, so sharing global resources, meaning that they're not independent tasks anymore, right? Usually, in the context of real-time embedded systems, well, we're going to use some variables to represent the registers, which in turn represent the sensors, actuators that the different tasks may be sharing. All right, so if we think of the different sensors, actuators, we can also think about the different modules that are present inside the microcontrollers, such as the ADC, for instance. So imagine if we're using two different analog sensors, with two different tasks, right? So each of these tasks should use the ADC in order to get the analog reading from the sensor. But we have to make sure that they're not doing it at the same time, or else we're gonna get gibberish. Fair enough? Alright, so yeah. So in order to avoid interference and get gibberish readings, we need to control the access to the shared global resources. Fair enough? The good thing about it is, instead of reinventing the wheel, all you have to do is use whatever mechanisms are offered with the RTOS, right? Because the RTOS will guarantee, the resolution or resolving any resource conflict that might stem. Alright, before getting to the flashbacks, to last year's OS Force and digging deep in your memory, right? To think about the different mechanisms that you might use. I'm gonna introduce something that is extremely important in the context of RTS. Alright, so there's something that we call atomic updates. Alright? Sometimes updates, they need to perform together to make sense. So I'm going to use an example to try and explain what do I mean by an atomic update. So imagine that we have some reading about the level of a battery, right? And at the same time, we have a variable that represents the time updated of that particular level of battery. So if we take as an example your cell phone, or your smartphone now, you can think of whenever you're checking your battery level, it should correspond to the actual, now time of that level. And it's not from 2 hours ago, 3 hours ago, or this morning. Fair enough? So those two, you feel like they need to go together. It's either they go together or they don't go at all. Alright? So whenever we want to update using whatever functionality here, whenever we're going to update the battery level indicator here, so the variable here, we need at the same time to update the timestamp of it. Right? So they need to go together. And this is what we call an atomic update. This means that we cannot segregate, we cannot separate them. It's either they go together or they don't go at all. Fair enough? Alright, so updates, they must occur together in order for the data to be consistent and representative. So we thought of when we were talking about those atomic updates, we thought of the phone, for instance, because it makes sense to have, again, the actual reading of your battery level that is corresponding to the time now and not from 4 hours ago. And with the face-to-face lecture people, we spent some time trying to think of other real-life examples where this particular thing related to the battery is very consistent and representative as well. And some of you, they've come up with the idea of electrical cars, also known as EVs, so for electrical vehicles. And it makes sense in order to estimate the the next time to recharge your car in a charging station. It's a good thing to have an actual insight about the level of the battery, which is in the current time and not from a different time frame. And one last example, real life example that I'll be talking to you about, and this is what we consider the intelligent batteries, because they not only provide the necessary voltage or the juice in order to make a system run, but at the same time they can give you insights or indicators about the next recharge time and what is the actual level, etc. So the third and final example that we're tackling today, or we're mentioning today, is the context of drones. Fair enough. So in drones as well, because they're based on batteries, and here I'm showing you screenshots from a relatively old research project of mine. So here you can see a drone, fair enough, with 6 motors here, rotors, so it's a hexarotor drone. And the idea is it's an autonomous one, so all you have to do is to create what we call a mission plan, right? And to make the drone understand the path that it should follow. You need to specify the start point and the landing point, so the takeoff point and the landing point, and different waypoints that you might use throughout the path. And the whole objective of the research was to create a methodology in order to estimate early in the design phase any energy needs to know whether the drone is capable of following that path and getting to the landing point with enough energy, or not taking off at all. And if you're interested in that particular project, I've published a research paper, and there's a blog, and there's an article in a blog dedicated for drones that mentions my research, and you can read it. It's quite it might be an interesting one if you're interested in drones. All right, so let's go back to the atomic updates. And this brings us to the critical sections, where we mentioned it last year. There's something that we call critical region or critical section that we definitely need to protect, and the best way to protect it, and this is what you need to take note of, we're gonna use mutual exclusion. The whole idea is to make them mutually excluded. And the whole thing, we're going to see it as an example here. So imagine that we're having 2 different tasks. The first one is responsible for updating both the level of the battery and the time of when the battery level is updated. Fair enough. So it's a timestamp as well. And the second task that is present in the system is responsible for printing out those 2 variables. Fair enough. So basically, we need to make sure that whenever we're printing out here, we're printing out the level that corresponds to the correct timestamp. So a bad scenario here would be I update the battery level here, and for some reason I get preempted by that task here, and I'm gonna print the updated battery level, however, with the old timestamp. And I want to make sure that this never happens, because those 2 needs to be updated in an atomic way, right? And they're considered to be the critical region or critical section here. Fair enough? All right, so this brings us to what we're gonna call, and please, should take good note of that. This is what we call the synchronization solution. So whenever we need to deal with the issues of different tasks sharing the global, different global variables or global resources, we need to make sure that they're synchronized, the access is synchronized. So this is what we call the synchronization solution. Fair enough? Alrighty, so flashback to last year when we talked about operating systems, right? So the solution here is to use semaphores. Fair enough? So it is an object that is a primitive object that is made available by the kernel. So you don't need to define it on your own. All you have to do is use it as if you're gonna use the tasks. So you're gonna create them. You need not to define the whole thing. So it is there for you. All you have to do is to know how to use it, right? And the semaphore can change a task state. So the question that typical question that I might ask, and I do ask, is it does change the state of the task from what state to what state. So you can directly think of a task in the CPU executing, so it's in the running state. For some reason, it's trying to take the semaphore, which might not be available for that task. Hence, it will get blocked. So it will go from the running state to the blocked state, or the waiting state. You can call it whatever. All right. And another thing that is important, because it's a primitive object provided by the kernel, and the engineers who worked on that, they made sure that it is fast in the sense of it doesn't take a lot of overhead to deal with the semaphore. Why would that be important, and why would I mention it in my lecture slide here? So the whole idea is, you should never forget that we're in the context of real-time embedded systems, and time is extremely crucial, right? So the less time we lose doing some changes or whatever, using different objects, right, the better it is. This means that less overheads, no long overheads, and fast switching back and forth between the different tasks, etc. All right, and if you remember quite well, last year we mentioned a couple of, 3 types to be specific, of semaphores. Those are the binary, the counting semaphores, and finally the mutex. All right, so this year I need you to really grasp the idea that whenever we're gonna use or protect a critical section or critical region, systematically you need to think of mutex. All right, so please do note, take note of that. A mutex, you need to systematically think of a mutex whenever you feel like you need to protect a critical section. Fair enough? The binary and the counting semaphore, well, especially the counting semaphore, they're used in order to detect events or to count events. All right, so it is a fast way to count events instead of you personally creating a counting mechanism, for instance. And the binary semaphore is, for events, and it's halfway through between the counting semaphore and the mutex. Fair enough? And we're gonna see and try and understand why the mutex is so special, and why do I recommend it to be used to protect critical regions or sections. All right, so the keyword here is mutex. It has some ownership associated with it. This means that the only task that locks the mutex is the only task that is allowed to unlock it. All right, unlike semaphores. So if I take the mutex, if task 1 takes the mutex, task 1 is the only task that is allowed to give it back. We good? Unlike semaphores. Semaphores, they can be, locked, unlocked by different tasks. So mutex, think of it as a locking mechanism in order to protect the critical section. All right, systematically, you need to think of that systematically as if, as you think of, the different things to implement the periodic task, for instance, which is the perpetual loop and some sleep time, right? So critical section, systematically think of mutex. And the semaphore, it's more there for some kind of signaling mechanism in the sense of, hey, I'm done, you can carry on, something like that. It's not really it's not really meant to protect critical sections, right? I'm talking naturally about the binary and the conic semaphore. Alright, so let's see that. So critical section, right? So definitely we're going to use some kind of semaphore. So we have 3 types of semaphores. Am I going to use the conic semaphore? Doesn't make any sense because, yes, if I have multiple keys, so basically this one could enter. So problem not solved. Should I use a binary semaphore? Maybe that could be a good idea. So if I lock here, maybe this one can unlock it because a different task could unlock a semaphore, a binary semaphore. So no, it's not. It's a good idea, but it's not the best one. Well, the best idea, as I said, systematically critical sections, you need to think of the 3rd type of semaphores, which is in mutex. Fair enough? So all we have to do to protect the critical section is to surround it by taking the mutex or the semaphore, which is in mutex, right? And then giving it back here. Fair enough? What should I do about task 2 here? So I need to do a similar thing. So I need to attempt to take the mutex here, the semaphore which is in mutex, and give it back here. So that would happen. Let's check this out. So those 2 here are taking the semaphore which is in mutex, right? So a semaphore is a generic word to say whether it's a binary, conic, or a mutex. And in this case, we're going to use mutexes, fair enough, critical sections. So this would happen. I start first executing, fair enough. I'm going to take the mutex which is available, right? I'm going to start my execution here. So I'm updating the battery level. Whoops, imagine that for some reason, I don't know why, task number 2 has a higher priority than mine, right? So I'm getting preempted right after I executed the battery level. So task 2 will start its execution, will attempt to take the mutex, which is already taken by me. It's not available, I'm gonna get blocked. So the CPU would be back to me to execute the 2nd instruction here. Hence, the atomic update happened correctly. And then, once done, I'm gonna release the semaphore. This one will be signaled that, okay, the semaphore is released, so you can take it now. So it will take it, print out, the different variables here, and those variables got updated in atomically. So the correct, values will be on those variables here, and we're good to go. All right. And this is a flowchart of the things that I just mentioned. So this is what happened. This is true for a binary semaphore and for a mutex as well, because they're almost the same. There's only one difference between them, and that's that. And the difference is this ownership. All right, so let's see that. So imagine that I'm a task attempting to take the mutex or the binary semaphore, doesn't really matter. So is it available here? So best case scenario, yes, it is. So I'm gonna take it, right? So I'm gonna take the semaphore and continue my execution, right? Other possibility here is the semaphore available. Well, if it's not, so all I need to do is to wait on it until it's giving back. If it's what do you call it? A new text, but I'm gonna wait on the other text that has it, that locked it, to unlock it, right? If it's in binary semaphore, maybe some other task will unlock the semaphore that is locked by a 3rd different task, fair enough? All right, so this is the normal scenario. And I'm gonna wait on it until the semaphore is given back, right? So this is where I'm gonna unpen, take it on, this is my turn to take it and continue my execution. And there's a 3rd thing here. Where is it? So you can notice that there's something else here. Alright, so this is the normal given we get, and this is the norm scenario, and what would that timeout be about? Alright, so the timeout here is, imagine that a task is waiting on the semaphore, and it's waiting and waiting and waiting, and the semaphore is never given back. So the engineers, the RTOS engineers, decided to give you the possibility to set a timeout, saying that, let's say, some stupid thing. Let's say after an hour of waiting, if the semaphore is never given back, well, you can resume your execution without, the semaphore being given back. So you're gonna consider that, okay, this is the longest I can wait for the semaphore. If it's not there, tant pis, I don't care. I'm gonna continue on. All right. This kind of beats the purpose of using semaphores. Fair enough, especially in real-time embedded systems. So my recommendation is to set your timeout period to infinity. So this task will always be blocked until the semaphore is taken. Whoop! Someone might say that, hold on, maybe this task, because you remember your OS course, might suffer from starvation then. Fair enough, because if it's waiting on it forever and it's not given back, so this one will never execute. Well, yeah, there's another protection mechanism if something freezes in the system. And remember that we can use something that is more efficient and more globally used. And it is the WTT. Alright, so let's see now in the case of someone giving back a semaphore or a mutex in that case. So yeah, so all I have to do when I'm gonna give back the mutex or the binary semaphore, it doesn't really matter. If someone's waiting on it, if it's not the case, well, the semaphore is just unlocked and it could be sitting there waiting for someone else to take it later on, maybe the same task on its next iteration. And the other scenario here is someone is indeed waiting for the semaphore. So what would happen? I'm gonna use whatever task is waiting. I'm gonna give it to the whatever task is waiting for it in two different schemes. It could be either first in, first out scheme, in the sense of the first task who asks for the semaphore when it was locked, well, it's going to get it first. Or more efficient way, especially for real-time embedded systems, it could be the task with the highest priority. So the tasks in the queue, in the waiting queue, that has the highest priority. Well, this depends on the implementation, and you should always refer to the data sheet, right? So both of them are used, and you need to make sure which one is available for you to use. Alrighty, yep, some caveats. So yeah, a caveat is kind of some kind of a warning or danger or something. Right? So this is the English lesson for today. And the fun thing about it is semaphores, all types of semaphores are great, and they help solve a lot of problems or issues that might stem from the use of common global resources, so for dependent tasks. But life isn't that beautiful in the sense of there's always bad and the good, and there's always good and the bad. So that's the yin and the yang. So anyways, to make a long story short, what I'm trying to say here is something wrong, something bad might happen whenever we're maneuvering semaphores in an incorrect way. What could happen? What might happen? Let's find out. So some of you, again from the face-to-face lecture, thought of something extremely nice, which is starvation, fair enough. And we've seen that there's actually two ways, including the thing that I talked about today, to solve any possible starvation, whether to use the watchdog timer in a way or another, or to specify a timeout period for the semaphore, right? Although I do recommend to set the timeout to infinity anyways and use the watchdog. Yeah, so this is not this is a solvable situation. But what if we don't pay attention whenever we're um, manipulating semaphores? Something could happen, such as drum roll. Let's see. So again, you're having something like that in your final exam, let's suppose, and you're trying to understand the system here. So it feels like this is an ADC. Okay, so this feels like some hardware component. This is a DAC, so this feels like a hardware component, and the display driver. This is definitely a hardware component because it's display. So yeah, or the interface to the hardware component is really better. It's hardware, extremely hardware related here. And apparently, we have a couple of, well, to be more specific, we have 3 tasks here. The first one is a control task, a SysID task, and the alarm task. Fair enough, this one feels like it's not sharing anything with anyone, right? Good for it. Alright, so this one just and is the only task that deals with the display. Those two apparently they're sharing both the ADC and the DAC. So one independent task and 2 dependent tasks sharing 2 different variables. Systematically from now on, please, whenever you think, whenever you know that you're dealing with shared resources, systematically you should think synchronization and hence the use of semaphores. All right, so critical sections, directly mutexes, etc. All right, so let's see what might happen here. Right, so it's trying to understand what might happen. So the control task, yeah, remember, so critical sections, so we're systematically using mutex, so it needs both semaphores, which are mutexes here, right, to deal with the ADC and the DAC. Makes sense. So basically, I'm gonna try and lock the ADC, fair enough, and then I'm gonna lock the DAC, execute whatever here, the bunch of instructions that are considered to be critical, and then I'm gonna unlock the that's a weird way. Alright, so I'm gonna unlock that one and then unlock that one. I would have unlocked it the other way around. Doesn't really matter as long as I'm unlocking it. So we good? So this is the control task, and there's another task that deals with the ADC and the DAC as well, and that was the SysID, right? So this system identification or something like that. It's going to do the same thingy. So, whoa, good thing here. It's going to wait for the DAC first and the ADC. Oh, good for me. So I'm going to try and lock the DAC and try and lock the ADC, execute my critical section, and do the unlock dance later. Right, we good. So what catastrophic scenario might happen here? So let's think of it for a second. So the control task will start executing first. It will lock the ADC. Whoops, someone preempted me, and it's the SysID task that preempted me. So the mutex, the SysID will try to lock the DAC, and it will try to lock the ADC, which is already locked by that one. So this one will get blocked. The CPU is back to me. I'm gonna try and lock the DAC, which is already locked by that one. Oh yes, I'm gonna get locked as well, and this is what we call a crust locked, also known as a deadlock. Alright, so this is a more visual or visually pleasant schematic of the execution, and we can see the different resources. The only task that is locking this one is the alarmer. So we got, all right, so here we can see, let's say the controls start first. It will lock the ACD. What's an ACD? No, it's not. It's the ADC. All right, it's crazy. All right, and for some reason this one will lock the DAC. So it got preempted, it locked the ADC and it got preempted. This one executed and locked the DAC, and then it's attempting to take the ADC, which is already taken, so it will enter a deadlock. It will be locked, right? it will be blocked. This one resumes execution and attempt to take the DAC that is taken by the SI, and hence this one is blocked as well. And here we're waiting indefinitely for the DAC, and here we're waiting indefinitely for the ADC, hence it's a deadlock. The luckiest one is the alarm because it's an independent one that only uses the what do you call it, the display. Awesome. They also protected the display with the semaphore, so that it makes sense. And this is anything that might be shared, because for now it's not being shared, the display is not being shared, but sometimes maybe there's a fourth task that might use the display, so we need to protect it in a way or another using semaphore. So systematically, anything that might be shared, protected using the synchronization solution, aka semaphores. Alrighty, this was the first caveat. Now I'm gonna think of the second caveat. So let's see. Oh, I didn't correct it here. Alright, so this should be alignment. Alright, so think of 3 tasks now present in the system. Alright, so T1, T2, and T9, right? The priority of T1 is the highest one, the priority of T2 is the second highest one, and T9 has the lowest priority. Fair enough? So high priority, middle priority, and lowest priority. Alrighty, so apparently they're using a semaphore that is shared by T1 and T9, so we can assume that there's a resource that's shared between T1 and T2. Fair enough? And it's protected by a semaphore. Mutex, binary semaphore, most probably mutex. Right, so let's see the scenario here. Alright, this is an important one. So let's draw conclusions from schematic as the good engineers that we are, or future engineers in your case. So apparently we are seeing 3 tasks here. Yeah, obviously. And obviously the first one that is starting its execution is task number 9. So this one was ready first, so the only task in the ready, so it will start executing. And then it attempts to take the semaphore, right? So the semaphore normally is created unlocked, so it will take it till we have our semaphore here. And whoops, this one became ready here, right? So it will preempt task number 9 because it has a higher priority than it. Fair enough? It will execute a little bit and then it will try and take the semaphore. However, the semaphore is already in possession of task number 9. So what would happen here? Oops, I'm gonna get locked. I'm gonna get blocked. So in the waiting state now. If I'm blocked, now the CPU could be back to task number 9. So remember, it's just 2 tasks for instance on the system. They're all ready. This one's not ready anymore, it's blocked. So this one who got preempted, well, can resume until task number 2 that has a high priority than it, right, is ready now. So it will preempt it in turn and start its execution, finish up its execution, and then this one is still blocked, so the CPU will be back to that one. It will resume in its execution here, and the moment that task 9 gives back the semaphore, it will systematically get preempted because this one can execute now and it has a higher priority than task number 9. So it will systematically directly take the semaphore now, execute it, give back the semaphore because I'm done with it, and then execute whatever is left because I still have the highest priority, right? I am the highest priority task. And then once I'm done my execution, and only then task number 9 could finish up its execution. Alright, so awesome. So let's see. What is the caveat? The whole point is to see something that is bad. What's the bad thing here? Alright, so let me think for a second. And you can help me out. You can think out loud. So let's see. Right, so someone decided that task number one should have the highest priority for a reason. Yeah, maybe because the deadline of that one is needs to be respected, and the deadline maybe is short. So yeah, I gave it a high priority for a reason. I gave this one the second highest priority for a reason, makes sense, and that one the lowest priority for a reason, well, because I don't really care. I mean, this one has the most flexibility when it comes to the deadline. Alright, so what am I noticing here? Let's see. So this one should be the highest priority, and that one in middle, and this is the lowest one. So the lowest one finished execution last, so it makes sense. The second highest one finished execution first. Oh, and that one's finished execution second. This is bad, because this one should have finished first. So yeah, so what you observe here is task number 2 got to finish its execution before task number 1, and it doesn't make any sense because task number 1 should have the highest priority. So this one should finish its execution first. So because of the use of the semaphore, remember, this is a dangerous situation because stemming from the use of the semaphore, that one got delayed until it's finished to finish its execution. So this one became de facto the highest priority task, and this is a bad thing. And this is what we call in the literature the priority inversion problem. So it feels like as if task number 2 has the highest priority and task number 1 has the second highest priority, as if those priorities are inverse now. And you need to think of the possible solution for that, as you need to think of the possible solution for the deadlock problem. One of your colleagues suggested for the deadlock to do something in order. I'll go for that. That's a good one. And here one of your colleagues suggested that if you think of it for a second, the whole thing is what caused this is the fact that this task got preempted by that one. And in order to protect it from being preempted, what we can do is whenever it attempts to take the semaphore here, fair enough, and when it's preempted, then it's normal for it to get preempted by task number 1. And what would happen is when we take the semaphore, we need to make sure to raise the priority of task number 1 enough, task number 9 enough for it not to get preempted by task number 2. So what we do is we inherit the priority of the highest priority task that is meant to take the semaphore as well. Alright, so when this one tries to take it, and this one, you know, is denying it from the semaphore here, what would happen is I'm gonna raise the priority, so the priority will rise here. So it will inherit the priority of the task. This way, task number 2, when it's ready, it won't be able to preempt it anymore because task number 9 will have the priority of task number 1, which is the highest priority. So this makes sure that I will give it back really quick, right? And then this one can execute that next. Fair enough? All right. As promised, I'm trying to give you as much as possible some real life case studies, and today's case study is about the Mars Pathfinder. So this is the name of the mission that happened in 1997, and according to your colleagues, you were -1 or 2 years old. And the thing is, what you're looking at here is the space shuttle and the rover. So it had 2 different components. The first one is the actual shuttle, so the spacecraft, and it had a shape of a pyramid. And once it landed on Mars using the different airbags that you're seeing here, so to ease the context with the floor. And the rover went out of it, and you can see it. Well, this is the rover, but you can see it's over there next to a rock. And the rover is called the Sojourner, right? And it's next to a rock that the NASA scientists decided to call it Yogi, as in Yogi Bear. They say that it looks like the Yogi Bear character from the cartoon. I don't see it personally. But this is the Yogi rock, and it's a special rock because apparently it's a smooth enough rock to consider that there might be some volcanic activity that happens on Mars, or maybe some water that's helped in smoothing the surface of this particular rock. Well, to make a long story short, we have two different modules, so the static pathfinder and the rover, the Sojourner, right? And if I'm talking about this particular real-life case study, because something happened on Mars, and this is what we're going to try and comprehend and analyze today. So what happened on Mars? Was it aliens? I can only wish. No, it wasn't that. What really happened on Mars is, and here you're seeing a screenshot from partially from an email that was sent by someone from NASA, right? And you can see that it deals with what happened on Mars, right? So if we try to analyze it, and it's destined to a bunch of people, well, anyways, so if you try to read it and try to understand, for instance, by now, with your experience in embedded systems, you should all know, right? Now, I suppose that we're all on the same page here, that any embedded system is made out of hardware part, and there's some software part, and the software is made out of the application software and the real-time operating systems. Fair enough. So to make a long story short again here, so it feels like they're using a single CPU that controls the spacecraft, etc., etc. Apparently there's a bus, and there's a radio, camera, and if it's a bunch of, you can feel that, a bunch of sensors and actuators. Fair enough. Yeah, there's a sun sensor, evolved thrusters, etc. Fair enough. So I'm gonna go ahead and focus on the problem on the next slides, so we can try and understand them together, or the problem, trying to understand it is a solve problem together, and try to find a solution for it. All right, so let's see. So all right, so the application layer, so the different tasks, right, of the Pathfinder, they were scheduled by a VxWorks RTOS. So you all know what an RTOS is, and apparently the name of the RTOS that the NASA people use for the Pathfinder is called VxWorks. Fair enough, and it contains the kernel, which has the scheduler, so it makes sense, right? And the algo, or the mechanism used by this RTOS, is a preemptive one. Good for us, we already know what that is, and it's based on priority. Good for us as well, because we already know what's a priority-based scheduling is. Fair enough. So each task has an assigned priority, and it's determined by its criticality or urgency. They call it urgency. Good for them. All right. So this is the RTOS layer, and now the different tasks that we have. So there's a meteorological task, data gathering task here, and frequent. This means that it has some kind of frequency. It is infrequent, so it's a periodic one. It's a perpetual loop with some sleep time. Anyway, and it has a low priority assigned to it. Fair enough. Thread or task, doesn't really matter, and use information by something. All right, so it's using some kind of a resource here that might be shared, and the resource here is the bus. So we need to protect the access, or synchronize it with the semaphore, and this systematically we need to think mutex. All right, so one task to now, low priority, and it uses the mutex to access a shared resource. All right, whoops, there's another higher priority task now. All right, so there are higher priority threads, including a high priority one, and this one deals with the bus management. So yeah, it has access to the bus, hence it needs to use the same mutex that is defined for the bus. We good? So basically, up until now, we have two tasks sharing the bus, hence the mutex that protects the bus. One with a low priority and another one with a very high priority. We good? Next. So unfortunately in this case, and this is what NASA is saying, a long-running communication task, so that's a third task that has a higher priority than the meteorological task here, right? So it has a higher priority than the lower priority one, but a lower than the highest priority task. Fair enough? So it's a middle priority between the two. And it's preventing the bus management task from running. What? That shouldn't happen. And the thing is, because of that, the OS notices, well, it's able to notice that the bus management task is not executing, and we know this mechanism that makes the system know when it's freezing, or when it froze, so we can reset it, right, or restart it. Conclude that something has gone wrong in order to our system reset, and it is the case. So yeah, what is the mechanism that we use here that made the system reset happen? You guessed it, the watchdog. So they learned from the previous mistake with the Clementine. Alright, so yeah, this is the situation. It's a bad situation. So systematically, whenever we start running the system, the long-running communication task is preventing from, the bus management task from executing, hence not kicking the dog, hence making a total system reset happen. And the funny thing, maybe not funny in a ha-ha way, but the funny thing is that engineers, they later confessed, after they solved the problem, that those system resets did occur on the pre-flight tests on Earth. However, as we all do as engineers, as the good engineers that we are, they assume that it's only a hardware glitch and we're gonna cross our fingers and everything will be fine once the system is, sent to space. And they were in the complete wrong here. Anyway, so now that you know the description, what I'm attempting to do is to find out what the issue is. And you can have fun at home, try to illustrate the execution of the different tasks using a schematic diagram with the 3 tasks and to find out what happens. And you can feel that what happens here is some middle priority task is executing and not allowing the higher priority one from executing in a way because of the use of one semaphore, which is a mutex that is taken by the lowest priority task and didn't get the time to give it back. So yeah, this is a priority inversion problem, and you can illustrate it at home and try to do the priority inheritance solution for it. Alright, that's it for today. I hope to see you all soon. Take good care of yourselves, and ciao.